Welcome to the Euler Project, a series in which we use Clojure to solve the problems in the online Euler Project and then take them to the max. Euler 8 is a simple little search algorithm. All we have to do is find the 13 adjacent digits in this list of digits here that has the largest product. Now, how hard could that be? So the first thing we need to do is get the data file in here, and you can see that I've stuck it in data.txt. I just did a copy paste right out of the web page and dumped it right in there. So then the next problem is going to be to parse that. So, okay, that's pretty easy. I wrote a little test here that is going to parse an input, a basic input of a string with a 1 and a space and a return and a 2 and a space and a return and so on. And when I parse that, it should be the string 1, 2, 3, 4. And here's another test that makes that a little bit more interesting. You know, 1, 2, return, 3, 4, 5, return, 6, return, 7, 8, space. And that should return 1, 2, 3, 4, 5, 6, 7, 8. So it's just getting rid of the line breaks and the spaces and putting that together into a string. And here's the code over here that does that. It's not at all very difficult. We take the incoming text and we split it by lines, and then we map trim throughout. And then we apply stir to all of the resulting lines. And that gives us what we want. And in fact, let me just run the normal tests. Okay, fine. So those tests work, and you're actually seeing all the tests run, but we're just kind of interested in these at the moment. And then the next test is to read the actual input data, and that's pretty easy. So we just slurp the data.txt file in, we parse the input, and then we make sure that there's 1,000 characters in the data. So that's pretty good indication that we've got the actual data, and you can see that the test actually passes. Okay, next, we need to prepare the data into digits. So right now I've got a string of characters. What I really want is a list of digits. So I've got a few little tests here that make sure that that works. I do the degenerate test first, of course, right? Making sure that if we do a string to digits of an empty string, then we get an empty list, and if there's just a 1 in there, we get a list with a 1 in it, and if we've got a string with all the digits in it, we will get all of the digits in a list. So that's nice, right? And you can see that that test works as well. Okay, well, what do we have to do after that? Well, now what we need to do is take a sliding window. A sliding window, in this case, it's going to be 13 elements long, but I made it a variable, so you could do 5, you could do 6, you could do 4. And then that window has to slide along the array of digits, and that will allow us to take the product of each window. Right? So not very difficult. So let's gather the groups. We call this gathering the groups. Sliding the window is the same as gathering the groups. And degenerate case first, right? We're going to make sure that if we've got an empty list of digits, no matter what the window size is, we're going to get an empty list of groups. And then if we have a list with 1 digit in it, and we're going to gather groups of 1 digit, well, then we're just going to get a single group with the number 1 in it. If we gather groups of 2, but our list only has a single digit in it, then obviously we don't have any groups because the group size is larger than the digit size. And here we're going to gather 2 out of the digits 1 and 2, and of course that's just going to be a single group. And now we're going to gather the groups of size 1 from the list 1, 2, 3, and that's going to give us 3 groups, 1 digit each. And finally, we're going to gather the groups that are 2 wide from 1, 2, and 3, and that's going to give us 1 and 2 and 2 and 3. I hope you understand that. How do we do the gather groups? Well, we're just going to hang in a little loop. So if the group size is larger than the remaining items, then we exit with the groups. Otherwise, we just recur with the rest of the items, and we append to the groups the next group size chunk. Right, so pretty straightforward. And if you look down here, you'll see that that test passes as well. Okay, well, what's the next thing to do? Well, the next thing to do is to try the sample project. The Euler 8 problem told us that the largest product in the groups of 4 was 5832. And so, okay, we should just try that, and obviously that worked. And in fact, here's the code for that. Find the largest product of group size n within the digit array, and okay, we're going to gather all the groups together, so here's all the groups, and then we're just going to compute all the products, and then we apply max to the products, and that's pretty much it. And you can see that 5832 did come out, and here is the answer for the 13. I actually computed this before, and then I stuck it in there. Right, and it runs the test. And the whole thing runs very quickly, you know. Looks like 56 milliseconds, and that's probably just the startup time. Right, so pretty simple, pretty straightforward. The problem is solved. I guess the video is over. Now, I suppose you could complain about this algorithm. It certainly looks like it uses a lot of memory, right? Because it's gathering up all those groups and then gathering them into products and then pumping all those products into the max function. But you have to remember that Clojure it uses lazy evaluated lists, you know, lazy lists. And if those lazy lists are working properly, well then maybe this isn't actually using very much memory at all. Anyway, that was just a little too easy, so let's see if we can't make it harder. So let's maybe find the largest product with a group size of 30. And if we run this, well, let's see what happens. Oh, heavens, we had some kind of horrible failure. And if we look up here, we will see, oh, we had a long overflow. So we are blowing up the long integer here. Well, I mean, that's easy to resolve because it turns out that Clojure will not automatically promote integer math to big integers, but there is an operation you can use that will automatically promote, and those are the quoted operations. If I put a quote right here, then that multiplication will automatically promote to the next biggest up number, right? Big integers and things like that. So let's see what happens when we run that. Oh, heavens, look, it actually computed something. And this is the result of group 30. So these are the 30 numbers in that list that have the largest product, and that there is the largest product. Well, aren't we clever? Clever indeed, but this has all been a bit too easy. So let's grow that group size up to, I don't know, how about 100 digits? Sure. I mean, we can do 100, pretty straightforward. We're just going to bump that group size up to 100 and run it. So let's give that a shot, shall we? We'll just run that and see what we get. And, oh my, that's interesting. The product, the largest product with 100 digits in it is 0. Oh, but of course, right? Because if any of the digits in there are 0, then the product is going to be 0, and therefore there are no strings of 100 digits that don't have a 0 in them in that text data. Okay, well, all right. I guess that's kind of a non-problem, isn't it? That kind of puts a limit on us, doesn't it? Because as we grow the group size, well, eventually the odds are that we'll hit a group size in which every group of that size has a 0 in it. I wonder where that limit is. Okay, well, what we're going to have to do is write a new function, which I'm calling here find the longest product. And we're going to have that function return the longest product we could find and the group that caused that largest product. And then we're going to check against nil so that we can see the answers. And here's the find the longest product function, and it's simply going to loop from 1 and accumulate the result. And how does it work? Well, we find the largest product starting with that group size 1, and then if that's 0, well, we've found the longest one that has a 0 in it, and we're going to want to return the one just previous to that, which is why we return the result, right? So the result is the previous one. And so if we haven't found it yet, we recur by incrementing n, and we return the product and the group. So yeah, that's going to do it. This is the previous result here, and okay, let's run it. Let's run it. Yeah. Okay. Wonder what we're going to find. Okay, that was a pause in there, wasn't there? And oh, it looks like 69. 69 is the largest group of digits in that data that does not have a 0 in it. Okay, and well, since that's true, let's just find out what the product is. And the product is going to, oh my, that is long, isn't it? And the product is going to be, Jiminy Christmas, that's a big number, huh? Okay, and let's just pop that in there. This is how I did all of them, and now if I run this, all the tests should pass. Man, that took a long time. Boy, that took like 1.7 seconds. Wow. Should it really be taking that long? I mean, I guess we are doing a lot of multiplications in there, and it's multiplications of big integers, so yeah, I guess it probably is taking a long time. I wonder how we could speed this up. How are we going to speed up multiplications? Well, do we actually have to do the multiplications? I mean, all we have to do is determine the greatest product. So, is there a way to determine the greatest product without computing the product using multiplication? This was my father's slide rule, a more elegant tool for a more civilized age. It's all based on logarithms. You see, you multiply on a slide rule by adding distances. Logarithms. Logarithms. We can add the logarithms of the digits together, and if the sum of the logarithms is greatest, that would be the greatest product. Oh my God, I'm smart. Jiminy, I am just so crazy smart. Man, wow, I am a smart guy. Okay, so I'm not going to change the tests at all, because we're just going to change the algorithm and the same test should pass. So over here on the algorithm side, first thing we do is we compute a list of the logs of all 10 digits. Okay, that's pretty straightforward, right? So list of the logs of all 10 digits, that's fine. And then we've got a nice little function here which will take a group of digits and turn it into a group of their logs. Okay, now finding the largest product. So that begins the same way. We're just going to gather up all the groups. But now we're going to make sure that there are no zeros, right? Because when you take the log of 0, you get infinities, and you can't multiply infinities, and so, or you can't add infinities. And so, okay, we're going to get rid of all the zeros. Yeah, I did do that, and then I realized I had to get rid of all the zeros. Okay, and then, okay, if there are no groups that don't have zeros in them, then we're just going to return this 0 here, because we're done. Otherwise, here's where it gets clever, guys. We're not going to multiply. We're going to add. We're going to add the logs of the groups. That's just so cool. And then once we have found the maximum sum, then we can go ahead and multiply just that group together to get the real number, right? So isn't that neat? I mean, come on. You gotta go with me here and tell me that's really cool. Let's run this test, right? Let's see. Didn't seem to go any faster, did it? I mean, it passed. It all worked, but it didn't actually go any faster. Maybe the multiplications is not the thing that was taking all the time. No, I'm not smart. I'm sorry. That was really dumb. You know what takes a long time? Maybe even more time than multiplying big integers? Adding floating point numbers. Because, you know, if the exponents don't match, you got to shift them around and do all kinds of manipulations. So adding floating point numbers might take more time than multiplying big integers by a single digit. Just might. I don't know. You know, with all the hardware assist that these modern processors have with doing floating point numbers, it's kind of hard for me to believe that adding to floating point numbers is really more expensive than multiplying a big integer, even if you're only multiplying that big integer by a single digit. Clearly, that's not where the time is going, right? The time must actually be in the algorithm somewhere. So I bet I could speed this up by changing the algorithm. Let's just walk through the list linearly instead of compiling all of these goofy, lazy lists. Okay, so once again, we're not going to change any of the tests here. The tests should still work, but the algorithm. You can see that I've made a huge change to the algorithm. Now it's a loop. Heavens, it's complicated, isn't it? So let's just walk through it quickly. The loop has 4 arguments to it. The incoming digits, okay, fine. The product of the first group, the current maximum, and the group itself. So the group that resulted in this particular product, right? So that's the incoming arguments to this loop. Okay, now, once we're in the loop, then we make sure that the current product is the maximum. So if it's not larger than the current maximum, we leave it alone. But if it is larger than the current maximum, then we move it to the current maximum. And if the current maximum has been moved, you can look at this and see that, oh yeah, that would mean it was moved. Then we're going to take the group and we're going to move it into it. So we will remember here the maximum group and the maximum product. That's what these two statements are doing. And then we recall the first digit. We're going to save that, and we get the rest of the digits. That's the next group over. Well, actually, it's the entire digit array with just the first one dropped off, right? And here's the next, and this is the next group over. And okay, fine. Now we do a little cond work here. If we don't have enough digits, right? So we're at the end and we don't have enough digits anymore. Then we're done and we just return the maximum and the group that solved the problem. And then we look to see if the very first digit was a 0. Ha! Now you're going to know why I did this in a minute, but okay. The very first digit is a 0, and if that's true, then we're going to recur with the rest of the digits, and the product of the next group and the current maximum in the current group. And yep, that makes perfect sense. And you know why? What? Well, if there was a 0 in there, then the previous product must have been a 0. And we don't dare do this next thing. So this next thing is only done if the first digit is not a 0. And the reason for that is that we are going to divide by that first digit and multiply by the last digit in the incoming group. You can do the math on this. You will understand, right? So we're not multiplying the whole group together. We're just dividing by the digit we're throwing away, and we're multiplying by the new digit that gets added on. Gosh, I'm so clever. I'm so clever, isn't that great? So with that, this should work. So let's run the tests. Run the tests, and we will watch this work. Yes! And it's not any faster. It's not any faster. That algorithm is not any faster than the other one, but it's a lot harder to read, isn't it? Why wasn't that faster? I mean, the number of multiplies is drastically reduced. I mean, through every circuit, we're just doing one multiply and one divide. So, I mean, we're not doing n multiplies per, right? So this should have been a lot faster. Unless maybe the multiplications aren't the issue. You know what? I think we'd better run a profiler. All right, so I've fired up a profiler here. This is this Visual VM profiler, and I'm going to run from the REPL here. I'm going to run my find longest product function 10 times. So let me start this up. Sampler go, yes. Okay, so now I'm going to hit the CPU button and I'm going to start my process. Let's let it do it. Go. Okay. Oh yes, you can see that we're definitely getting something going on here. We're collecting data. This is a sampling profiler, so just every few milliseconds it looks at the stack to see what's executing, and it compiles a statistical model. And then, okay, we're done. I can stop it. Lovely. And now let's go look at the hotspots. And the hotspots show me, oh, heavens, 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 heavens. What does it show me? All of the time, 84.4% of the time is spent in lazyseek.seek. And almost none of the time is spent anywhere else, like in the multiplication functions or anything else. I mean, the next largest one is pos. So, yeah, all right. Where is the time going? The time is going into managing the persistent data types in Clojure, particularly the lazy sequences. Okay, that's where all the time is going. Makes a lot of sense because I'm doing a lot of sequence manipulation, so okay, I guess that answers that question. And so there you go. I mean, whenever you think you know where the time is going, you're probably wrong. So before you optimize, profile. So how can I make this go faster? I suppose I could use Java arrays in Clojure. You know, Clojure lets you access Java arrays. Although, you know, maybe what I should do is, like we did with the prime factors, just write the whole thing in Java. That would make it go a lot faster. Yeah, that would make it go a lot faster. But I don't really need it to be faster at this point, because what I really need is for this episode to be over. Anyway, that's the episode. Hope you enjoyed it. Hope you learned a thing or two. But you're not going to want to miss the next exciting episode of the Euler Project. Episode 9, Pythagorean Triplets. you.